Move along. Okay, so tissue engineering is upcoming. So there is a lot of potential in the field of tissue engineering. So we'll touch based on how biomaterials are used. What are the various considerations for different kinds of biomaterials to be used as tissue engineering constructs or tissue engineering scaffolds or tissue engineering matrices. It's all synonyms: matrices, scaffolds, constructs. So they mean basically the same thing. Okay, bench to bedside. Okay, so I'll discuss what is bench, what is bedside, and the whole process of taking a potential biomaterial from the research stage to the patients, to the hospitals, to the clinics. Okay, future of artificial organs. So artificial organs are basically, if you manufacture in the lab any organ which is manufactured in the lab, not really from patients, not really from donors. Okay. What is the potential and how far we are in developing such artificial organs? Okay, so I will touch based on that. Spinal bone replacement is also a very widely used application for biomaterials. So we use metals, we use different kinds of software biomaterials to replace the backbone. Okay, so we talk a little bit about that. What are the considerations for ensuring that you have the appropriate biomaterial for, say for example, a disc replacement or a bone replacement, spinal bone replacement. And we'll talk a little bit about bioreactors. What are bioreactors? What are the functions of bioreactors? Why do we need to use bioreactors? And definitely we'll practice some questions. Just to make sure that you guys are prepared for the final exam. Final exam matters, right? It matters a lot. So I want to make sure that you guys have understood the concepts and are ready for addressing at least my portion of the questions. Okay. Okay, let's get going. So this is a question. Which of the following is natural biomaterial? What do you think? Lactic acid? We don't make acids in the body. So it's polyglycolic acid?
Obviously, it's
Polyethylene glycol?
collagen, right? It's
What do you think?
polyethylene glycol. Sorry, collagen, right?
What is the answer?
Collagen.
Collagen, right? So collagen is derived from glandular sources. When I mean glandular sources, it's animal source, it can be a human source, it can be animal source like porcine, pig sources, cow sources, sheep, goat, whatever. Okay. So collagen is a natural biomaterial that we derive from living sources. Okay? Guys. Okay?
What is this?
Which of the following transplants has the highest
Why can't you
chance
put
of
this in your
success?
fucking slides?
What do they? Allograft, autograft, xenograft all have similar success rates.
Allograph.
All have similar success rates?
I wish this was the finals.
No?
Why you really use your silence?
I'll just let
Allograft?
Allograph.
Allograft? Allograft? Why allograft?
Allogram.
No shit.
Why do you think allograft is the highest success rates of all these? Autograft and xenograft?
Come from the same person.
Pardon?
Come from the same person.
No, that is not allograft, that is autograft.
Okay, that must be autograph.
That was a good one. Okay. So yeah, so it's autograph because it is coming
Take
from
the
the
wing,
same
bro.
person. Okay, so even if it's coming from the same species, there might be chances that it may not be compatible to an individual of the same species. Okay. And xenograft, obviously we are very concerned about xenograft because it has a foreign origin. It has a foreign origin, so there might be immunological cases or incidents.
You didn't dig into for yesterday. 2 days ago.
You can hear me for an hour or so, then you can talk as much as you want. Okay?
Yes, sir.
So just hold on for an hour, and if you have any questions, ask me. Okay, if you have any questions, ask me. Okay, so it's So it's autograft, right? So it has the highest chances of. Okay. Okay. Do you guys know this person?
Who's this?
Do you guys know this person?
Tony Stark.
He's called one of the fathers of the field of fish engineering. Is Professor Bob Langer from MIT. Okay, so they consider that if there is a Nobel Prize in fish engineering, he is the person to get it. Okay, but there is no Nobel Prize for fish engineering as such. Okay, but he is very well known in the field of fish engineering. Okay, there are few other people, few other researchers and scientists, but he is one of them. Okay, okay. So what is the field of fish engineering? It plans. What is the intent to use different kinds of biomaterials to replace organs or tissues. Okay. Why that is a problem? Because getting an appropriate donor is a huge issue. We have sufficient donors. How many of you want to donate one of your kidneys? Or your liver, right? So there are not very many donors.
I don't need
a
any.
patient
I
who's suffering from
die inside. I
liver
don't need
cancer,
it. The person they take mine probably die
okay.
more.
They need a replacement kidney. They need a replacement liver, and there are no donors. Okay. So there have been numerous incidences where patients have been waiting for years for a donor, okay, a donor organ, and it never came, and they died. Okay. So the idea of fish engineering is to replace a natural organ or natural organ which is not functioning properly, which is not functioning efficiently, with a man-made or synthetic organ which functions as close as a natural organ. Okay. So that is basically the intention of the field of fish engineering. Okay. So, and again, fish engineering is interdisciplinary, so we need expertise or different kinds of people with different expertise. So we need chemists, we need biologists, we need mathematicians, we need dentists, we need basic research scientists, we need biological engineers as well. Okay. So it's again an interdisciplinary field. Okay, as I mentioned, just imagine that liver failure, kidney failure is no longer a problem because we have found the solution, and the solution is developing an artificial organ in the lab or maybe a factory. We can manufacture it in the factory. We have to ensure that it's of quality, it's sterile, so on and so forth. But we can manufacture in the factory or in the lab, okay, and then place these kind of devices or these kind of artificial organs inside an actual patient. Okay, to replace a non-functional or a malfunctional organ or tissue. Okay, just imagine one day. And in my opinion, we do have few such organs. Say for example, we have artificial skin. Okay, do you guys know that we have artificial skin in the market which you can buy? So patients who have burn injuries, okay, patients who have skin cancer, so you can actually buy artificial skin
It can be black.
in the market. It's available in the market. You can go and search. So we
Black
have
people
my
have
dream to be a nigger.
So Michael Jackson is
so it is
artificial
not
skin.
as good as the natural
nigger.
skin, but
Okay,
it
so isn't it just
performs the
plastic
function.
surgery?
What is important is the performance of the appropriate function.
Technically
We do not
just plastic
want,
surgery.
do not expect that it will be very
So it's
handsome
plastic surgery
looking
and
or it will look exactly like the natural skin and stuff like that. But we want to ensure that it performs like the natural skin. Okay, even if it may not look like the natural skin. Okay, so we have some of those in the market. Okay, but what about the complex organs? Skin is not that complex, right? So what we talk about when we talk about complex organs, say for example, heart, okay, kidney, liver, these are very, very complex organs. So we do not yet have a replacement or artificial replacement of those very complex organs. The brain is very complex. Okay? So we do not have a strategy or a system to replace those kind of organs with artificial organs. Okay, even though it looks like, it sounds like science fiction, but in my opinion, maybe in the next 10, 15 years, we should have artificial organs which are very complex. Okay, so a lot of researchers in our department, in other departments as well, they are working all around the world. So there are quite a few researchers who are working in this particular area, including Bob Langer from America. So a lot of potential. We are yet to see lots of artificial organs in the market, but in the next maybe 10 to 15 years, we will see or start seeing artificial organs in the market, which will replace malfunctional or inefficiently functioning natural organs. Okay. Okay, these are some of the organs that we plan to replace: the stomach, kidney, liver, heart, brain, lungs, and so forth. So all of these are very, very complex organs. Okay, none of these are very simple organs. So it takes a little while, but eventually, I'm keeping my fingers crossed. We'll have a strategy to develop these kind of organs in the lab and make it compatible with the human system, and then replace organs. Okay, so how this happen? We want to ensure that the artificial organs. So the artificial organs, it's not a 3D structure, or it's not a mechanical device. It's not an artificial hip which has the function of holding on to the mechanical stress. Okay, so these are organs like lungs, heart, kidney. They do not have a necessarily mechanical function. They have the more physiological function. They perform a function within the body. Okay. So ideally, these organs should have the cells of the patient himself or herself. Okay. Now, why is that? If it's a foreign cell, what will happen? There might be immunological responses. Okay, we want to make sure that there is no potential immunological response. So to counter that problem, we use the patient's own cells who is requiring the replacement in the first place. Okay. So we take few cells. Now we cannot take a lot of cells. What will happen if we take a lot of cells?
You die.
We may not have access to so many cells because the patient already has an organ which is not functioning properly. If we take a lot of cells, the organ will stop functioning in its entirety. Okay? So we do not take all the cells or many cells, we take few cells. But what we'll do with those few cells? We grow these few cells in an artificial environment to make sure that we have a huge number of cells. Okay? From maybe 1,000 cells, we need 1 billion cells. Okay? So we need few cells from the patient to ensure that there is no immunological response, but we need to grow these few cells into many, many cells. Okay? And eventually, we have what we call the 3D scaffold. Okay? It's a 3D structure. I will explain in a subsequent slide. It's basically the home. It's basically a 3D matrix which will be the home of the cells. And the cells will grow and multiply and eventually cover the whole 3D structure. So that is the basic concept of 3D plant. So once we have the scaffold, once we have the matrix, okay, then we place the matrix into the patient. Okay, and eventually, what is the expectation? There will be good communication between the artificial organ and the biological system of the patient. Okay. So the cells replicate, reorganize, and form new tissues. So with the new cells, from the old cells, there will be more and more of the new cells because they will multiply, they are dividing. Okay. So eventually, the cells will replicate themselves, so they will multiply, they will reorganize, and they will eventually form a new tissue. Okay. And they will eventually take over the whole 3D structure and start functioning like the normal heart or the normal kidney. Okay. So this is the whole idea of tissue engineering. Now, if it consists of a polymer, now many times we do not want a foreign body in the foreign substance in the body. If it's a polylactic acid, a polyglycolic acid, we do not want these to remain in the body for a long, long period of time. We ideally want the cells of the patients to replace the whole organ in its entirety. Okay, so the 3D external material, polylactic acid, polyglycolic acid, is gone, and it has been replaced by the patient's own cells. Okay, eventually performing the complete function of the heart or the kidney, whatever the organ. Okay, name it. Okay, so that is the whole idea of the field of tissue engineering. So now you can understand there are few things, or quite a few things, which we want to ensure before we can use a particular biomaterial. It needs to have the proper chemical properties, proper physical properties, proper mechanical properties, even proper biological properties that matches with the need of the patient. Okay. So, so this is the first thing. You need the cell. Now, in the exam, I don't expect you guys to remember all the parts of the cell. Okay, so it's just for your knowledge. So this is a typical cell. It can be any cell. It can be a muscle cell. It can be a cardiac cell. It can be a bone cell. Whatever the cell might be. Okay, it can be a liver cell. It can be a heart cell. Whatever the cell we are talking about can be of this this type. Okay, so it's basically the living part. It releases the various enzymes, it releases various factors which perform the function of the whole organ, right? So basically the organ is a complex structure which consists of not one type but multiple types of cells all working together in conjunction with each other. They communicate with each other and eventually leading to the function of the whole organ. Okay. So it produces ECM. What is ECM? Basically extracellular matrix. So for example, cells in the skin, they perform, they release collagen. Okay, collagen is a protein, and it's also called the extracellular matrix. Okay, it performs the mechanical function of the skin. So the skin or the bone has some mechanical function, right? So it stretches, the bone is hard, and so all these comes from part of the collagen. So collagen may be a factor that is released by many of these cell types. Okay. So biomolecules, various kinds of biomolecules are released by the cells. Okay. So a specific function. So what is stem cell? You guys might know stem cells is undifferentiated cells which can be led into the path of performing a particular function. Okay. Stem cells are they don't have a specific function. Okay, unless they go into a particular direction. So stem cells can become bone cells, stem cells can become kidney cells, stem cells can become heart cells as well. But stem cells in general, as such, they do not have any well-defined function, but they can perform the function of a particular tissue depending on their situation. Okay. Now this is the scaffold. What is the scaffold basically? The scaffold is basically a 3D structure. Okay. It's basically a 3D structure, and why it's important? Now the cells need a surface to hold or to attach. Okay, the cells cannot multiply on by itself. Okay, in thin air. The cells typically don't multiply in blood. As the blood is flowing, the cells don't start multiplying. They need typically the surface to attach themselves. Okay, once they attach, you recall from the last lecture, I mentioned the cells flatten up once they attach to the surface of a particular biomaterial, and they started multiplying. They start releasing all the factors, all the biomolecules, and they started functioning like a typical cell. Okay. So the scaffold, the 3D scaffold, performs that particular function. It allows the cells to home in, to make its home. Okay. And then eventually it starts attaching, proliferating, which is multiplication, grow larger, from a small cell to a big cell. Eventually they divide in the middle to make two cells, and eventually the process goes on. So basically this is the home for the cell. The cells will attach onto the nooks and crevices of this particular 3D structure. Okay. So this is the function of the scaffold. It provides the mechanical support, structural support, and the shape. Okay. So when we are talking about replacing the whole organ, we have to ensure that the scaffold looks like the organ itself. Okay. You cannot have this kind of thing and place it in the place of the heart, right? So the scaffold should ideally look like a heart, and then the cells can grow in the scaffold, and eventually they take over the function of the whole heart, okay, or the kidney or the lungs, whichever. So the morphology or the structure or the shape is important, and so is the function. Okay, so it typically is what the scaffolds do. It allows the cells to home in. It allows the cells to grow and multiply inside the scaffold. Okay, so they have to be biodegradable and biocompatible. What is that? What is biocompatible? It is compatible to the biology of the system, right? So for example, if a particular biomaterial is biocompatible to my biological system or human biological system, we have to ensure that it does not provide any untoward events. It does not create any immune response. Okay, so that is basically biocompatible. It's compatible with the biological system of a particular organism, okay, or a particular species. They are not intended to stay in the body forever. So typically, when we talk about the classical theory of tissue engineering, you do not want this kind of scaffold to stay in the body forever. Okay, they stay in the body, but and after some time they release what we call, from for example, this is polylactic acid. Okay, so after a while the polylactic acid will become lactic acid, so it degrades into its monomer. Okay, and eventually there is no 3D scaffold. It has completely been replaced by the native cells. What is native cells? Cells from the own patient. That is basically the native cells. So not intended to stay in the body forever. They stay for some time and eventually are replaced by the native cells of the patient. Okay? And using the cells will function just like that. I mean, they don't need anything else. They need what we call the signaling. Okay? The cells are signaled to perform a particular function. Okay? So signaling is also very important. Signals tells the cell that you start releasing the growth factors or start functioning like a typical cell. Okay? So signaling is also very, very important. It has been shown by different researchers, including some of my own research, that mechanical stress, electrical stress, these are potential stimulators. Okay, so if you put the cells under mechanical stress, they perform a little better. Okay, as compared to the static conditions. Okay, so external stimuli at times promote cell growth. So external stimuli may be mechanical stimuli, may be electrical stimuli. Okay, so this is how typically the cells work. So these are the three components: cells, scaffolds, and signaling of the biomarkers. Okay, so these are the three basic components which we keep in mind. But we need to keep in mind that these are the classical. This is the classical theory of tissue engineering, and these are the three components of the field of tissue engineering. Okay. Any questions?
I need a weekend.
You guys are very quiet. You're listening intently. Okay. Okay. Okay, so now scaffolds, they can be of different structure. Okay, now scaffold cannot be of the same structure, all the scaffolds. They, under the electron microscope, they may have different structures. So this is more organized, so this is like different thread-like structure. So depending on what kind of application we're talking about. Okay, if it's a replacement of the heart tissue, okay, the bone tissue, we need a structure which is very robust. Okay, it is mechanically very strong. So we might need maybe something along this. Okay. So if it's we need a very porous structure, so we want to replace the skin or the heart. Okay. We need a porous structure like this one or this one. Okay. So basically, depending on the application, remember, depending on the application, we use different kinds of biomaterials. So biomaterials application is dictated by the usage. Okay. What I mean by usage is the mechanical properties of the organ that we plan to replace, the biological, even the physical and chemical properties of the organ that we plan to replace. So this is architecture of various types of scaffolds. Okay. Now they can be made of different materials. Okay. Lactic acid, glycolic acid, polyethylene glycol, bone cement, you name it. Okay. So now, the design criteria. So it looks typical of a trachea, right? The windpipe that we have. So you see, this looks typical like a trachea. And what are the things that we are looking for in a construct like this? We want to replace the trachea. So what are the things that we need to be aware of? What are the things in the scaffold that we want to have? Okay. So it has appropriate mechanical and physical properties. The properties should be in tune with the requirements. Okay. So the properties cannot be too different from what we really need, because that will defeat the whole purpose. Right? So we need a structure, we need a material which is in line with what we need. Okay. So it should have appropriate mechanical and physical properties. It promotes cell adhesion. What is promoting cell adhesion? It promotes the attachment of the cell. Okay. So unless, as I mentioned, unless it really attaches with the structure, many cells do not function. Okay, so we have to keep that in mind. Proper degradation rate. So if the degradation, so if it's a polymer which has the property to degrade in a biological system, we have to ensure that the rate of degradation is optimized. Okay. What if it's not optimized? If it's too slow, then we won't be having the structure in the first place. It will go away very soon. Okay. And if it's very hard, the degradation rate is very slow. In those cases, the bone cells or the heart tissue cells will have difficulty attaching there, because there is not enough space for it. You have basically only the surface. Okay, if the degradation rate is very slow, you basically have the outer surface for the cells to attach. Just imagine, okay, so degradation rate is very slow, there is the initial 3D construct, and it's not degrading at all. So it's basically the cells have the outer surface to attach. And many times it's again defeats the purpose. Okay, so bottom line is, the cells need a optimum environment, optimal 3D structure to attach, okay, before they can function appropriately. Now, toxic degradation products is very important. Cells, we need to ensure that there is minimal, if at all, any degradation.
How can you just add these in the slides? I was saying.
Why is that? What will happen if there are a lot of toxic degradation products coming out from the biomaterial? Polyglycolic acid. So when it degrades, it releases what? Glycolic acid. Okay, if the glycolic acid is too dangerous, too toxic for the cells, it will cause damage to the cells, right? So we have to ensure that the degradation products of the polymers that we use are not toxic to the cells, or at least they're not very toxic to the cells. Okay. Now, polylactic acid, polyglycolic acid, rather than lactic acid or glycolic acid, they will have some side effects. Okay, they're not something which our body is used to, right? So there would be some side effects, but that should be minimal, right? If it's too bad, then there would be again very bad inflammatory response. So there would be inflammation and fever, and there can be other side effects as well. Okay, so ideally the toxic, the byproducts should be as minimal toxic as possible. Okay, otherwise there would be significant side effects. Integration in the surrounding tissue. Now, you cannot expect a whole organ to stand by itself. It needs to communicate with the whole biological system. Okay. Now, if it's artificial heart, if it's artificial liver, it needs to communicate with the rest of the body as well, right? It's not a standalone organ by itself. Okay. It needs to communicate with the other organs, other systems, other blood, whatever in the body. Okay, so it needs to have a proper communication system. So it needs to integrate with the native tissue as well. Okay. Now the foreign tissue, if it stays in the body for a long time, you have to ensure that it actually is highly biocompatible, and there is no chance, if at all, any of the release of towards byproducts, and it integrates with the surrounding tissues pretty well. Okay, seamlessly. And as I mentioned earlier, there should be minimal inflammatory response and almost no immune response. Okay, so so if there is a significant immune or inflammatory response, that will reject the whole artificial organ or the synthetic material. And eventually, what will happen if the body rejects a particular organ, artificial organ? If there is a significant immune response, you know what is what we call the prophylactic shock. Okay, the patient will undergo a shock because the body has immediately rejected the foreign material, and there is a potential that patient might die. Okay, so to prevent a prophylactic shock, which can potentially kill the patient, we have to ensure that there is minimal inflammatory and immune response. Okay, so far so good. Any concerns, any complaints, anything you want me to go over again? Anything which is not very clear? Okay? Okay. Okay, now I mentioned the host. Which is the host? The host is basically our own biological system. And the guest is basically the foreign material. So there has to be a good communication between the biological host, which is the patient himself or herself, and the foreign material. So they both affect each other. Okay. So they both affect each other. So as I mentioned, here, recall from the last lecture, mitosis, back to mitosis. When we put the implant into the bone, so this is a foreign material, this is the host material, this is the biological system, this is the foreign material. So they need to communicate properly. Okay, and there is a potential that the host might create some problems for the material, and also the material will create some problem for the host. Okay, so it's both ways. Okay, so that's the reason they have to be highly compatible to each other, highly like. They have to like each other. How do we like each other? But by telling each other that we are compatible. Okay, and we can do a
Kanina so easy
variety
eh.
of tests, variety of assays to ensure whether or not a particular foreign material is compatible with a particular biological system or not. Okay, so the bottom line is they both affect each other negatively. Okay, and we need to be aware of that, and at times we have to deal with that. Okay, so. Okay. Now let's take a particular example. You guys know this? Another of my toys. What is this? I thought I have used artificial lip a couple of times. Let's use a different model. So what is this? This is a backbone, right? Now you have to understand the properties of this particular tissue. It has bone. It also has some kind of cartilage, which is a softer tissue. So the properties of the two parts of the whole, this particular system is different. One is a bone, which is a hard tissue, and one is the softer one, which is the cartilage, something around that. Okay, so you need two different biomaterials to come together to perform the function of the spinal bone. Okay, now, you can actually see here, if we can replace the whole thing with a hard tissue, hard biomaterial. For example, titanium implant, okay, or titanium alloy. It does not provide the flexibility because titanium is hard; it cannot move, right? So titanium has to come in conjunction with a softer material, which will provide the flexibility of the like similar to the natural tissue. Okay, so it can be some kind of a hydrogel. It can be something along those lines. Okay, but nonetheless. The bone has to be replaced by what we call the titanium screws and plates and so on and so forth. Okay. So this is titanium. If we need to replace only the bony part, then we use the titanium. In those cases, the middle part, which is the disc, is perfectly fine. Okay. But if we need to replace the disc as well, the whole structure, then we need a much more complex combination of different types of biomaterials. One having a function which will replace the hard tissue, which is the bone, and then a softer material which will replace the disc. So basically, so again back to the very point that we need to identify what exactly we want to do, what exactly we need. Okay, and depending on that, we need to choose the appropriate part. Okay, that is the point I'm trying to make here. Okay. Okay. So as I mentioned, the host and the biomaterial they perform different functions, and we want to ensure that the toys are very helpful, right? It helps explain a lot of different things. So I very often use this thing. Okay. So you see this particular thing. This is what we call the liner. This is what we call the vestibular cup. Okay, so the white thing is the vestibular cup. You can see everyone? Okay, so so the white thing, I did not get a bigger specimen because this is exactly how it looks. Okay, I wanted to show you this is the size of an artificial hip. Okay, and this is actually the size of the natural bone itself. Okay, so so we can actually see the host affects the biological system affects the material. And the material in turn affects the host as well. So both of them affect each other in a negative manner at times. Okay. So we need to be aware of that thing. So host responds to biomaterials. So how does the host affect the biomaterials negatively? Okay. So how does this bone or the blood affect the foreign material? Okay, they do, right? So what might happen? Protein absorption. This is the local at the site of implantation. So if this is implanted right over here, so at the site of implantation, what is the various events that are going on? Okay, so protein absorption. Is it a good thing or bad thing? That is what happens, right? But if it's a wrong protein, okay, that becomes a problem. Okay, the protein absorption on the surface is a natural process. Happens, but if it's wrong protein, then that becomes a problem. So typically we engineer the surface to ensure that one particular or few particular types of proteins only attach onto the biomaterial surface. Okay. Protein absorption, coagulation of blood. Is it a good thing or bad thing? We want coagulation of blood at the site of implantation. We do not want, right? Because it will have consequences. Okay, so this is something which should be prevented. Coagulation of blood. Platelet adhesion to the biomaterials. At times, we have platelets in the blood, right? So at times, platelets adhere to the biomaterial surface, which is not ideal, which is not really desirable at times. Okay, so it needs to be prevented. Hemolysis, sometimes if it's very nasty biomaterial, it's not very compatible, it can actually break the blood. It's what we call hemolysis. Lysis is breaking apart and hemo is blood. Okay. So it's breaking apart the various cells or various components of the blood. Okay, just imagine, it's supposed to do good, and then it started doing some nasty things like breaking the blood or damaging the blood in some manner, okay, which is not really good. Inflammatory response. Okay, it can cause some very nasty inflammation. What is inflammation? It can be redness, it can be fever, it can be very itchy, okay, redness, all those things. So that is inflammation. So there can be inflamed tissue around the site of infection or the site of implantation. Okay, so that again is not very desirable. And definitely infection is a concern. If it's a implant, okay, what will happen if this is not sterile? If this is not sterile, there would be concerns about causing infection. Now, if there is infection, you have to put in antibiotics and stuff like that. Okay. So typically, we have to make sure that this product is of quality. Okay. It is manufactured with safety in mind. Performs well, and then it's sterile. Why it needs to be sterile? Because it is an implant. It needs to go into the system where it is coming in contact with the blood, coming in contact with the cells and the tissues. Okay. So it's very important that it is sterile so as to prevent any chances of infection. Okay. Any questions? Any concerns? Okay, so systemic response. What is systemic response? Now, in the previous slide I mentioned it might be local response at the site of implantation. Okay. At the very place where you are placing the foreign material. But there are certain things which might happen all throughout the body. Okay, now system is the whole system, the whole biological system, whole human being. Okay. Now, what are the things that might happen? Formation of thrombus. It can formation of thrombus is basically a blood clot which can form at a place which is quite far away from the implantation site. Okay, it can happen somewhere distant. Okay, but nonetheless, it can happen somewhere in the system. Embolism, a tiny particle might travel through the blood or the lymph system. We have the lymphatic system as well, right? So we have the connective tissue, which is the blood. We have the lymphatic system. So a tiny piece of the biomaterial can transfer through the blood vessels, and that can cause a lot of problems. And hypersensitivity. Some patients are sensitive to a particular material. Okay, so say for example, this is made up of cobalt chrome alloy, right? So some patients have been shown to be very sensitive to cobalt metal. Okay, if we put cobalt metal, they react vigorously. Okay, because the system does not want to accept cobalt as a biomaterial. So in those cases, patients show signs of hypersensitivity to a particular material. It can be an element, it can be an alloy, whatever. Okay, so hypersensitivity. Elevated elevation implant elements in the blood. So as I mentioned, if this is a cobalt chrome alloy, right? So this is cobalt chrome alloy. So it has been shown that the cobalt or the chromium ions that are released from this particular material is present at an organ which is very far away from where it's implanted. So if we implant it here, we find the cobalt chromium elements in the urine, for example, or in the liver. Okay, so it is found at a place which is quite far away from the initial place where it was implanted. Again, do you think that's a good thing? That's very nasty, right? Okay. So we don't want those ions, cobalt ion or chromium ion, to travel throughout our body and be placed in some other places. Right? So that is again very nasty. Okay. So, lymphatic particle transport, as I mentioned, there is the particle can be transferred either through blood or through the lymph system. Okay. And the systemic toxicity, the patient might it might be like an immune response. There is a vigorous untoward effect that is explode the whole body. Okay. So that is basically. the toxicity in the whole system. It can happen throughout the body. So these are some of the things which might potentially happen. It does not necessarily happen because we have to prevent it in the first place. And it might happen either at the site of infection, inflammation, or the whole RHN system. Okay, so now skin tissue engineering. So, say for example, we want to have so this is the part of the skin. We take certain cells and we expand these cells in the lab. Okay, so we expand these cells in the lab, and nonetheless we have the scaffold here. So it's a mixture of the scaffold in one place and the cells from a patient in another place. Okay, so we grow the cells artificially in the lab, and then we place the cells onto the scaffold. Okay, so now there is a combination of the cells which are present in the scaffold. They are attached and growing inside the scaffold. Okay, at times we put in some biological factors to promote the growth of the cells, depending on what tissue we are talking about. Okay. And then eventually we place this thing onto the patient surface. Okay. So this is how we typically grow the skin, artificial skin. Now it can be applicable to other organs as well. The strategy is something similar. It's not the same, but the strategy is somewhat similar. So epidermis, it can be other part of the skin as well, depending on what we want to replace. So we have the skin cells and we have the scaffold. We grow the cells outside. Okay, and there might be different things that we need to add. We don't really have to worry about those. There are different things. And then we do an expansion. Expansion is basically growing few cells into many cells. Okay, I mentioned growing maybe 1,000 cells into million or a billion cells. Okay, that's what happens here in the petri dish or in the lab. Okay. Now we use bioreactor as well. I will come to that in the next few minutes. Okay. And then we have the scaffold. Put the cells onto the scaffold. The cells are growing. You can see they are growing as well as they're multiplying and dividing. Okay. And eventually we put this thing into the patient. Okay, to replace the whole thing. Do you think the skin, artificial skin, looks exactly like our natural skin? It does not grow. It's very weird that it does not grow here. Okay, so you can actually see that there's a difference in texture, difference in color between the natural skin and the artificial skin. Okay, it does not have any cells to grow here and all those things. So it is devoid of all those properties which a natural skin has. But nonetheless, what is good thing is performs the function of the natural cell. It protects the underlying tissues. Okay? It prevents infection. That is more important. Which is more important, looks or the function? Looks. Some of the looks.
All other skins.
Looks are more important than function. Okay, so I think function is more important, right? As long as it performs the function of the tissue, I don't really care how it looks. Right?
What about the skins, bro? What about the
So that
skins?
is how things happen. Okay. So now, nutrition is very important. We need to ensure that the cells have nutrition. What will happen if the cells don't have nutrition? They will die, right? Now, this is the scaffold. You can see the scaffold is like a 3D structure. Okay, this is a scaffold. Now, it looks like it's pretty thick scaffold, maybe a couple of centimeters across, right? So, so what is the effect of nutrition? Okay, or the flow of nutrition? Now, you can see here, this is the scaffold. This is the cell at the very center. So, the cell not on the surface, but at the very core of the scaffold. Okay, so we define the core as a bulk. Bulk is actually the inside. So these are two surfaces, two areas. One is the surface, which is exposed, everything. Okay, and the bulk is which is inside. Okay, now if you see the surface, which is right over here, the cells have access to the media. Now this is static. The cells are the media is not moving. Okay. The problem is if the media is not moving, the cells will not have access to the media. Now what is media? Media is basically the food. Okay, the media has the food. As you worked in a particular research lab where you're growing cells, okay, you put the scaffold in the media. Media may have lots of protein, antibiotic at times to prevent infection. Okay, so it's basically what the cells need to grow. Okay, so if the media is static, there would be cells which do not have access to the growth media. Okay, the cells will start dying. You can see the red cells, they are dead cells. So dead cells are red. Okay, so and here we have mostly green cells. The green cells are live cells. So it's very important that the cells have access to the growth media, because the growth media is basically the food for the cells. Okay, so unless you have the cells, all the cells having access to the media, many of the cells will die, and that will defeat the whole purpose of the field of tissue engineering. So we need to have the confidence, we need to ensure that all the cells have access to the.
Yesterday BME welfare package.
Okay. I've been shouting too much. So is it okay if I take 5 minutes off and we'll start in 5 minutes? Okay. Now, if you have any questions, you can come up to me and ask me. Okay. We'll start in about 5 minutes.
I jump queue. Ciao.
This can be
Wait, is it a break?
Any questions for me? Anything that is not clear? Anything that you want me to rephrase, explain? Okay? Okay, so far so good? Okay.
If one of your
Now,
method sequence is rejected, the whole method is rejected.
what is translation? And what is bench and what is bench
I really
side?
don't understand.
You guys know? What is bench? Bench is basically the research labs. Okay, we do the research in the labs. That is bench. Okay, that is basically the research component. Okay, now the research is not by itself sufficient for taking a potential device to the patient. Okay, it needs to be research and then it needs to be approved and not processed. And the bedside is basically
it's
where it
to one,
reaches the
sorry.
patients.
Yeah,
Okay,
the
so
sequence
bench
2
is
is rejected,
research,
hence my opinion
bedside
part 2
is
is rejected.
access of the devices
It's mainly
to
to
the
one, mainly to
patients.
one.
So that is basically
Mainly to one is the one that you want to mainly.
What is translation? Translation is basically the whole process.
Listen, I'm trying to
Translation is basically
I don't know
taking
what
a
audio
potential
maps
product
to-
from the research phase
Maps
to
to this
the
one, not this one.
patient. That is translation.
But then the whole thing is
So
rejected.
translation is from the bench to the bedside.
Fuck them, just
So guys, clear on that?
apply, don't care them, don't
That is
care them.
bench to bedside.
I
Now,
tried it.
how do we do that?
So then how? Then
We start
this one still-
our experiments
no,
with
I face. I go there,
something
take
which
really,
is
I
very,
then
very
mapping
basic
like
in
that.
the lab.
Yeah, I cannot project
So
transfer.
some of you who might have
just apply it.
work in the labs, we do
Because
some
right now
what
I'm
we call
doing
the
one.
in vitro test, right?
So I
So
do
we
one
put
on one.
the cells in the scaffold and stuff like that, and see the response, whether the cells grow, multiply,
It should be made to
transform.
one if I'm not wrong. I remember I
I
Okay.
think it should be made. I assume it's going to be
And
made. So that's
once
the same
we
thing as
have
module.
satisfactory results from this particular aspect, then we take
All the
the
pre-map
next
one
step, which
is
is,
all in
putting the scaffold or the biomaterial onto an animal, okay, a small animal, typically a small animal. And if it satisfies, if we get good results, okay, then we take it to a bigger animal, rabbit, guinea pig, and eventually maybe the horse, and eventually human. Okay, so you can actually see the whole process when we start off with the bench to the bedside. So this is the bench, and eventually it takes the whole process to the bedside.
Read mouse.
Okay, so how long do you think it might take from bench to bedside for a typical medical device? Many years, quite a few years. Okay,
Ask the
and
BME
especially if it's a new biomaterial, it can be even longer. Okay. If it's a known biomaterial, it can be
I know
shorter
engineer,
because many times FDA would have approved it for a particular
Yeah.
application. We know it's a good biomaterial.
I don't really wanna go, I'm not tired,
But if it's
yeah.
a novel material, it's a
Let's
new
ask
material,
Jia how you mean
the
now.
steps can be significantly longer. So, and it requires investment of hundreds of millions of dollars. Just imagine, hundreds of millions of dollars to make sure that we have the appropriate biomaterials for a particular application, from the bench to the bedside and translation. That's why it wrote a long, bumpy road to translation. It's not very easy to bring a product to the market, to the patients, to the hospitals, to the clinics. It's not very easy. It takes a long time. It needs deep pockets. It needs to have lots of money, lots of resources, lots of well-trained engineers. Okay, to ensure that we are not stuck with the basic research, but the basic research shows us the path to eventual application of a particular biomaterial. Okay, so this is. Now I mentioned IRB, ICA. What is IRB? Can we just take a potential biomaterial and put into the patient? What do you think? I prepared my very nice looking, very good looking biomaterial in my lab. And anyone who wants to volunteer, I want to place that into that particular person. I haven't done any test. I haven't done any safety test, anything. But the thing looks very, very promising. It looks very nice. It is hard. Can I have a volunteer? No one will agree, right? So RRP is basically if you want to involve human patients, if you want to involve human subjects into your research, clinical trials, you have to have your protocol approved by what is called the IRP, Institution Review Board. Okay. And ICA, if you want to work with animals, any animals, okay, not humans, you have to have it approved by the ICA. So it's an institutional animal care and usage committee. Okay. So bottom line is if you want to work with humans, you have to get it approved from the IRB. If you want to work with animals, you have to get it approved from the ICA. Okay. So keep these things in mind. These are very useful information. Okay, so who approves my protocols if I want to do a clinical trial? If you want to do a non-clinical trial, non-clinical is basically animals. Okay, so these are the two bodies. Do you think we have something like that in NMS? We do. We have ICA committee, we have IRB committee. Many times if you eventually use animals for your, not just us, but animals, the whole animal system, you will have to interact with these. Okay, so just let me know. Okay, so bench to bedside, there are certain things we have to identify what is the unmet clinical need. You cannot just manufacture a material for nothing. Okay, it needs to have an appropriate usage. You have to define where you can potentially use your research biomaterial in. Okay, under what clinical circumstances people might need your biomaterial. Okay, what is the unmet medical need that is going to satisfy? That is basically what is the clinical unmet need. Now, do you think the big manufacturers, the MNCs, Johnson & Johnson, so on and so forth, they make the biomaterials or research biomaterials for societal purpose? They want to serve the society or what? What do you think? They're very concerned about the people and about the suffering, so they want to invest billions of dollars in developing biomaterials. No, they want to have access to a market where they can sell the product, make the profits, and put part of that profit back into the R&D. Okay. So they have to have an appropriate market. How many patients need this particular biomaterial? Okay. How much would be the selling price of this particular biomaterial? So these are different concerns for the MNCs. So when I was with Johnson & Johnson, that they manufacture different kinds of biomaterials, especially orthopedic, dental. Okay. So that is a big concern.
Johnson &
How many patients do we can find who might need these kind of biomaterials? Okay. Scalability or attractive for investment. Okay. Attractivity for investment, someone has to invest. Okay, if it's a research lab, then we need angel investors or someone who has a big amount of money. Okay, so that they can invest in our development process. And eventually, when it becomes marketable, when it reaches the patient, we get the profits, then we can share the profits. Okay. I do the research, you provide the money, and when we develop the material, when it goes to the patient, whatever the profit we get, we share. So someone has to invest. Scalability. We talk about scalability because these kind of devices should be accessible to many people. It's not only the rich. It's not only for the famous. Okay, who can pay. So it's very important that we can scale it up, okay, from one to a few to numerous, to many, and then eventually to the whole body. Okay. So scalability is very important. Okay. It should not be only for the patient famous, it should be for each and every patient who needs these kind of medical devices. Okay, or these kind of biomaterials. Okay. Approvability, as I mentioned, who approves the medical devices in Singapore? Who approves? H.
PB.
SA, Health Science Authority,
Who
right?
lost?
So they approve medical devices in Singapore. Who does it in US? FDA, right? So Food and Drug Administration. So they approve medical devices in
Do you really
US,
need to know this?
and HSA does it for Singapore. Now each country they have their own regulatory body. Okay, each country they have their own regulatory body, and you cannot just create a manufacture something in your lab or in your garage and
Does anyone else?
sell it to patients. You cannot do that. You cannot just sell it
Oh,
to
no,
patients
this day,
without approval.
DA.
You need to have the approval for
They-
selling it to the patients.
What was the
Now,
US one
what
again?
would FDA or HSA look for when you provide the documentation to them for approval?
Oh,
The ideal
I
thing
see
they will
all
look for is the safety, and they will look for the performance or efficacy, that the device is safe. Because you put the device or the biomaterials into the patient, it should not kill the patient, right? Because if there is an immune response, there is a potential that it can kill the patient. So they will ask evidence, show me the evidence. Show me the evidence, show me the experiments that you have done to ensure that this particular material is safe when it's implanted into the human body. Okay, so this is something they will look for. And also, if you claim that your device can perform a particular function, how will you ensure? Show me the evidence. It's all about evidence. Okay, so show me the evidence that it is actually performing, it's effective, it's performing its intended function. A cardiovascular stent is supposed to perform like a cardiovascular stent. It's supposed to have a certain function, right? So you have to define the function, and you have to provide the evidence by different kinds of experiments to show FDA or HSA that it is actually doing that, what it is intended to do. Okay. So safety and effectiveness is very important. And what is follow-up? Follow-up is basically when you put the device into the patient, you see the function. Okay, you see the safety aspect. And if there is any problem
passes all
with
regulations.
regards to the
Sub 60%
functionality of the device,
patients
you
dies.
follow it up.
Surprise
You
Pikachu
address the
face.
concerns of the patients, you address the concern of the medical fraternity. Okay, the clinicians, the hospitals has to ensure that the device performs
Passes all protocols
like
and
it
puts
should.
into
Okay,
patient.
performs perfectly
Patients
fine. There
dies,
is
the
very
first
few,
Pikachu's
if
face.
at all any safety issues. There is very few, if at all, any performance issues. So it's performing fine. It is very safe for the patients to use. Okay, so these are the things that FDA would ask for. Okay. So these are some of the natural and some of the synthetic polymers. Again, I don't expect you guys to memorize this slide. Okay, so for my part of the exam, nothing to memorize. I will,
No, you will
talk a little bit about that.
All
So
biomaterials
polymeric,
are-
so chitosan, alginate,
biomaterials
you just
doesn't
need to
exist.
know what are some of the, at least few of the natural biomaterials and few of the
It's
synthetic
like, I don't know how to.
foams, hydrogels,
Because I want to take
naturally
picture
collagen, hydrogels,
but
some
not
have
because
ceramic,
any
resorbable
right?
maybe,
Yeah,
which is
this
dissolved
is a
by
period now.
hydrolysis and so forth.
Should we-
Okay.
Okay.
You can actually
Yeah.
change various aspects.
Omega Lul.
Okay. Okay, so again, these are some of the
Star 201 is a defunct
polymeric
mod.
scaffolds. As I mentioned, there are numerous polymeric
Because I want to take
scaffolds.
this, but I need this.
This one really
Few more minutes and then we are done.
Don't
Then
look
you
at
can
me,
come back and
come
do
on, Joey.
Okay, few more minutes. Okay, so these are again some of
I'm
the
dead.
polymeric biomaterials which are used to make
I have
different
you
kinds of
seen- I saw you.
scaffolds for different applications.
I have you seen,
Again,
I will G.
not for you
That's
to
very
memorize, but it's good to know. It's good to know what are some of the
Yeah, it's the same,
biomaterials
because it's new.
and
It says
what are the
updated.
potential usage of these kinds of biomaterials.
Oh.
Okay. And how fast or how slow they degrade the biomaterials.
This is the last 3 slides.
bioreactors are very important. Many times I mentioned we can take only a very small number of cells from the patient. Because if we take too many cells, the function would be, the patient might die because the organ is already not functioning properly. So we can only take very few number of cells. Now what we do with the cells, we grow the cells in the bioreactor. Bioreactor is what? It's a machine, it's a small device which can grow small number of cells into numerous cells. Okay. So this is a typical how it looks like and what are the various functions. So you can have the cells here, right over here. Okay. You can have the cells over here. Okay. And flow of liquid is basically the media, the growth media. The cells need something to eat, right? Just because their cells does not necessarily mean they don't need anything to eat or drink. They need food. Okay. So this is the inlet, which is the food for the cells which is right over here. So this is the good food, and the cells also release metabolic waste products. Right? So the cells also have metabolic waste products. Okay. So these are released from here. So this is input, this is output. This is the inlet, this is output. Now as I mentioned, the cells also need some mechanical stimuli. Okay. The cells do need some mechanical stimuli. So we have some kind of a stirrer. Okay. When it stirs, it provides some mechanical stress onto the cells. And that promotes the growth and division of the cells. So this is the stirrer. Okay, and we have to ensure that the pH is appropriate. If it's too acidic or too basic or too alkaline, the cells will die. Right? So the ideal, it has to maintain an ideal pH. It has to have a particular concentration of oxygens and so forth. Okay. So basically what it's doing, it's trying to mimic the in vivo condition. Okay, what's actually happening inside the body. So it's trying to mimic the in vivo conditions in an in vitro environment. So this is outside the body, but we're trying to create a situation as to what actually happens inside the body. Okay? So this is the very fundamental design and the function of the bioreactor. You will find bioreactors in most tissue reactors, most biomaterials labs, okay, which work with cells. So this is a very, it may be a very small one, it may be a big one. In industry, it can be a huge one, okay, much taller than me, okay, depending on the need. Depending on the need, you can have big bioreactor or small bioreactor. Okay. Okay, no questions.
They say you want to cover the whole
Let's see.
scope.
Scaffolds are not intended for
I put it to S lah, such that it does not affect my
structural
units.
support.
Like
Hold
what?
the
How
cells
will
in
it
place.
do lah? Because
Cell system forever. Promote cell attachment and proliferation, which is not the answer.
what the fuck is this?
A. Did I hear A?
C.
C.
Alright, so anyone who thinks it's not safe? Okay, the scaffolds are supposed to degrade over a controlled period of time and eventually let the cells grow, right? So it's not supposed to stay in the system forever. Okay. Biocompatibility means
D.
made by biological methods. Biocompatibility made by biological methods.
That's a D if you ask me.
From
So
biological,
I hope this is the exam, man. This is the exam I'm sure you
biodegradable,
want.
compatible with
Everyone will
biological.
get full marks.
Yeah, I won't get A anymore.
Biocompatible means you can see.
Some fuck.
D.
Who next A, who next B?
It's D.
What is it?
D for donkey.
STFU hard
So
already.
yeah, so it's compatible with
These two good
living
already.
system. Any
It's just a
system. It
nerve.
can be a human system, it can be animal systems also.
Just want it to end.
Yeah, I actually agree. Thanks for doing this.
Okay, I'm done. One small suggestion or tip for the final exam for my portion, do not try to memorize my slides.
I'm still going to memorize.
None of my questions would be involving a lot of memorization. None. Okay? So what I want you guys to do is to understand what I explained. Okay? And my questions would be more on how to understand the basic concepts and how to analyze. Okay, that's the reason I put in a lot of pictures and there is very few text in my slides. Okay, so do not try to memorize my slides. Okay, my questions would be all based on your understanding of the fundamental concepts and the analysis and applications. Okay, so absolutely nothing to do with memorization. Okay, so I can assure you, if you see the question, you will realize nothing to do with memorization. If you don't memorize anything, but understood what you are not, it is just fine.
Ask the Yuki.
Okay. Okay, I enjoyed the module. I enjoyed teaching you guys. If you have any questions, my office doors are always open. You just have to send an email to me.
Give some comments. How do you find this lecture?
Okay, thank you. And